Hey everyone, welcome to another crash course. Today is going to be about stalls. Crash Course 103 assumes that you are familiar with angle of attack and relative wind. If you are not familiar with angle of attack and relative wind, please go back and revisit Crash Course 102. I've drawn an airplane with a black line and a red line. The black line is forward momentum and relative wind. Forward momentum is where the airplane is actually going, and relative wind would be the equal and opposite direction of the wind impacting your face. When an airplane is in level flight, most people assume that the black line and the red line are the same. In reality, they're not. Even though an airplane is in level flight, the red line, which is the chord line, is typically 2 to 2.5 degrees greater than the black line. This is called a positive angle of attack. In the next few slides, I'm going to show you a progressive increase in the angle of attack. This is the starting baseline angle of attack. This would be a further increase. And this third one is the essential subject matter of today's lesson. This angle of attack that I just drew represents 17 degrees, which is typical for a stalling wing. I know it looks more like 45 degrees, but I needed to exaggerate the illustration so I could actually draw and show you what's happening. Black line, red line, same as before. Now the only difference is what happens if your red line actually goes further. Once you exceed your stalling angle of attack, so if the red line goes any further, you enter what's called a stall. Any further increase in angle of attack will result in less coefficient of lift. The wings stop working. The red line is pulled away from the black line so much that the airflow is beginning to separate on top of the wing, meaning that your wings are not developing any more lift, therefore gravity takes over. A lot of new pilots initially think that you can only stall when the nose is aimed towards the sky and the ground is beneath you towards the ground. To be technical, that's true only for 1G stalls. I have 4 airplanes drawn, and the red lines represent their pitch attitudes. Which one do you think has the higher angle of attack, top to bottom, 1, 2, 3, 4? I didn't draw the black line, the relative wind, so there's no way to tell. The scenario I have drawn here is the pilot diving for the ground and yanking back on the control stick in order to arrest the descent. Now, since we have our relative wind, or the momentum vector, we can calculate our angle of attack. Obviously, the bottom aircraft has the highest angle of attack. It's almost 90 degrees. I'll speed through the rest. I can understand the pilot's uneasiness and his instinctive desire to pull back on the stick, but all that will do is accelerate the stall, and he'll still crash into the ground. Stalls can get somewhat dangerous when landing. Because you're so close to the ground, it doesn't give you a lot of room to recover. This airplane has a pitch attitude that's almost level to the horizon, but it has a trajectory, the black line, that's aiming for the runway. This is a very normal approach and landing. This next airplane is a situation that you don't want to find yourself in. The nose of the airplane is aiming upwards, but the black line, the trajectory line for this airplane, is aiming short of the runway. This airplane is not going to make it to the runway. The reason why this is happening is because the pilot does not have enough kinetic energy. The pilot is pulling back on the stick, hoping that the black line will return to normal and get him to the runway. This will not happen. The reason it won't is because all the stick does is change the direction of the nose. The engine thrust is what's designed to propel the airplane in the direction that the tails are pointing it at. Thank you for watching my Crash Course series. If you have any questions or comments, please write them in the section below. And stay tuned, I'll have more Crash Course series coming up soon. Bye-bye.